This video, we'll be talking about the normal distribution. And the question is, what is a normal distribution? And I want to point out that the definition of normal is not the same in statistics as it is in what you think in real life. In life, normal means something that's common. The normal distribution is not called the normal distribution because it's common. It just happens to be one that we see. I guess in some ways it's somewhat common. But it just means that it's got this basic bell shape. So a normal distribution is something that has kind of a bell shape. It's symmetric, but it's more than being symmetric because as it's got a peak in the middle and then it drops off on both ends the same amount. And so we get, from data, we can get this histogram and then we can fit a curve above it. And that curve that we fit is called the normal curve. Notice the normal curve does not cut across the axis. It basically stays along the axis. It'll get closer and closer to the axis, but it has this basic shape, and we call it a bell-shaped curve because it kind of looks like a bell. So what we're going to do is talk about the characteristics of the bell-shaped curve. In this, if you look at this, you're kind of what we call concave down here, which means that you can't pour water onto it and it stays. And then it's concave up here, which means you could pour water on it and it kind of pulls. And you've got these places called inflection points where that actually occurs. The center of the curve is actually known as the mean. So this center falls right about the same place as the mean is, in fact, exactly the same place. And if you go one standard deviation below and one standard deviation above, you get these inflection points. And so the peak is the center, which is the mean, median, and mode, because in a normal curve, because of symmetry, all three are the exact same place. Again, it's symmetric and it's bell-shaped. It tapers off as you get lower and lower, get farther and farther along the x-axis in both directions, and it will taper off the exact same because of symmetry. This side and this side are exactly the same. One standard deviation beyond the mean on both directions, again, is that inflection point. And then we have something called the empirical rule. The empirical rule, I don't particularly like all that much, but it is there for you to see. And what it tells you is that 68% of the data is within one standard deviation. So if you look at the amount of data that's in here, if you were to take a bunch of people's heights and put all their heights onto a normal curve, 68% of the people's heights would be in this one standard deviation away from the mean. And the empirical rule kind of tells us that. It's approximate. It's not perfectly 68%, but about 68%. If you went farther out, another standard deviation out, so this distance is also one standard deviation, and this distance here is also one standard deviation, you get to two standard deviations because you went two standard deviations in both directions. And the empirical rule tells us that 95% of the data is between these two. So again, if you took everybody's heights that falls nicely on a normal curve, 95% of the heights would be about two standard deviations away from the mean in this area. And then the last, if we went one more out, so we go out to three standard deviations above and below. Again, this distance again is standard deviation. So we're now three standard deviations above it. You think we have all the curve, but we don't because it does keep going along here in both directions. And so we actually say that about 99.7% of the data is within three standard deviations of the mean. So those are the basics behind it. Here's a picture, a little bit more of that idea. So here's 68% of the data is one standard deviation away from the mean. 95% of the data is two standard deviations away from the mean. And anything that's over here, there's not a lot of data over here. 95% is a lot of the data. So if you think about only 5% is out here, and so we actually say that if we're beyond two standard deviations in the mean, then you're considered unusual. So this would be an unusual value over here and over below. Again, 99.7% is within three standard deviations. Notice you have most of the curve shaded, but you see here and on the other tail here, you have a little bit of the graph. So you have about 0.3% of the graph beyond there. So that's kind of what the empirical rule sheds in kind of graphical way. An example is, let's say we look at the resting heart rates of people. It happens to be that these are normally distributed with a mean of about 70 beats per minute and a standard deviation of about 15 beats per minute. These are population values, so that's why we use the symbol mu and sigma for mean and standard deviation, because they are in fact population values. The way we got them is we took a bunch of samples and we graphed them and we found them, but we decided these must be close to the values. We'd like to find the percentage of resting heart rates that are greater than 70 beats per minute. So what I want you to think about is drawing a normal curve. So let's draw the normal curve. All right, and the center of the normal curve is your mean. So coming back up here, your mean is 70. So there's my mean of 70. And we want to know what percent of the people have a resting heart rate that is greater than 70. So that's talking about in this area over here. But because of symmetry, the whole curve is 100%. So above 70, which is half the curve, must be 50%. Let's go ahead and put the standard deviations in here. So if we're going to add one standard deviation, that's 70 plus 15. So you're going to add 15. And you get 85. And then we're going to do the same thing. We're going to subtract one standard deviation. So we're going to subtract one standard deviation. 70 minus 15 is 55. And the problem asks us what percent is less than 55 beats per minute. So remember, between here, there's 68% of the data using the empirical rule. Because of symmetry again, if this is 68%, then this one must be, this area here must be half of that. So half of 68 is 34%. Now, because of symmetry again, half of the curve is below 70, just like half the curve is above 70. So half the curve is below 70. So if this is 34%, then this must be 50 minus 34. And that gives us 16%. So you play a little bit with some algebra here, just kind of putting things together. But that's where we get the 16% here. Greater than 40 beats per minute. So let's go another standard deviation below. So again, subtract 15 from 55. That gives me 40. And let's go the other direction just to kind of keep things organized. 85 plus 15 is 90. So between 40 and 70, again, the empirical rule tells us that that's 95%. So then, kind of playing around with this same kind of concept, if this is 95%, what is over here and here? Together, those two must be about 5%. Because if it's 95% is between those two, 5% must be above and below. So if 5% totals above and below, then just one of them is half that, again, using symmetry. So 5% divided by 2 would be 2.5%. And if this is 2.5% here, this is also 2.5% here. Now the question was, how much is greater than 40 beats per minute? So 40 is this whole 95 plus the 2.5. So 95 plus 2.5 is where we get the 97.5. Because we did 95 and then we added 2.5. All right, so now let's go a little bit farther out. Let's go 3 standard deviations. So I need to make my number cover a little bit longer here. So 3 standard deviations would be 40 minus 15 would be 25. And again, just to keep things nice and neat here, add 90 plus 15 gets me to 105. And the empirical rule tells me how much is between these two lines. And because we're kind of running out of space here, I'll kind of just draw a line here. This is 99.7% of the data. It's between those two lines. So again, how much is in these last two spots, right? So how much is total in here? So total in there would be 100 minus 99.7. And 100 minus 99.7, I'm sorry, 99.5. Oh, my goodness, 99 point. Let's go look at the empirical rule. Remind ourselves what it is. It is 99.7, sorry. So 99.7. So 99.7. And that would give me 0.3%. So there's not a whole lot of data up there or down there together. So now the question is, how much is just in this one little spot? Well, again, because of symmetry, if these two together is 0.3, then this must be half of 0.3. So looking at that, this would be half of 0.3, which is 0.15. So this 0.15% of the data, less than 25 beats per minute. So now let's look at the standard Z-score. So we can also, instead of just looking at what percent, we can actually, and what standard deviations we are, we can actually find out how many standard deviations exactly is a number from the mean. So the way we do that is we take each x value, subtract off its mean, that kind of centers it, and then we divide by the standard deviation, which kind of takes out the standard deviation, tells you how many there are. So the Z-score is the number of standard deviations away from the mean that a data value is. We always use Z for it, which is traditionally what letter we use. So as an example, if we have a resting heart rate of, let's say, 85 beats per minute, then it's going to be 85 minus 70, the mean, divided by 15. 15 divided by 15 gives me a Z of 1. The Z of 1 is considered usual because, again, if we're outside two standard deviations, we're unusual. So -2 to 2 is the usual value. Oops. Means it's usual. Okay. Let's actually write that a little bit neater. So -2 to 2. Your Z is between those two values. We consider it usual. And you can actually say equal to. So usually you're not exactly ever equal to a number, but we can have that kind of thought. So let's look at 40. 40 minus 70 over 15. So again, remember, it's always the x value we're dealing with minus the mean divided by the standard deviation. So that's minus 30 over 15, or -2. -2 means it's below the mean. Positive means it's above the mean. Because it's between -2 and 2, including those two values, it's considered usual. Now let's say you have a resting heart rate of 105 beats per minute. 105 minus 70 divided by 15. 35 over 15 gives you 2.33. So that would actually be considered an unusual value, which means that this is something that would be considered unusual to have, and if somebody has a heart rate that high, they would be considered unusual, and maybe they need to look at what's going on. So that's how we can use the Z value to help us make medical decisions or other kind of decisions about a value of whether or not it's usual or not.